Hello, I'm Sophie Xhonneux. I am a scientist for machine learning at the ECMWF, and I am here today to talk to you about deep generative models in the context of the training course for machine learning for Earth systems modeling. The structure of today's lecture is going to be in 3 parts. In the first part, I will try to introduce the core concepts. What are generative models? Why do we care about them? And why are they non-trivial to build? In the second section, I'll talk about variational autoencoders, which are kind of a core generative model that is commonly used and that is useful to have in mind, even when learning about other generative models. And in the third, I will talk about a kind of topical score matching / diffusion, which is kind of gaining in popularity more and more. I encourage you to grab a pen and paper, pause the video, and go through some of the algebra or some of the kind of diagrams yourself in your own pace. Because I am talking to a camera, I can't take your questions live. It is worth pointing out that in this lecture, I will focus on the continuous setting instead of the discrete setting, and this has its own kind of properties. It's also worth saying that there's a number of things that I cannot cover just because of time. Some of the notable ones that you might have heard of are GANs or CRPS models. The kind of first core question is, what are generative models? The goal of generative models is to learn a distribution. You will denote this distribution with px, where p is kind of the probability density and x is kind of the sample. And the goal will be to do this with a neural network. And this neural network, we're kind of hiding it, but it has the parameters theta. And so we will denote the kind of learned distribution with p theta x. And the goal generally is that we can sample from this distribution. Sometimes we really care about having a specific likelihood number, so like a probability density number of the actual likelihood of a sample. But in practice, usually we care about samples, and if we want to kind of estimate how likely is an event versus another, we just kind of sample enough to get a rough ratio of the two. The kind of second question is, what information do we have to kind of learn px? And how might we can then use the neural network to generate the samples that we care about? There's broadly 2 classes. The first one, you might imagine that you have access to some kind of reward. This is common in a lot of AI for the science, such as biology or material science, or you might be able to estimate how good is a molecule or how good is a crystal, and then you use this kind of reward to compute a Boltzmann distribution over kind of what crystals or molecules you want to sample. This is not the setting that we care about today. Instead, we will kind of assume that we have access to a large data set of kind of example samples. Usually we will write this throughout this lecture as p data x. And you can imagine this, like for instance, ERA5 is such a data set which kind of captures the kind of global atmosphere state over many kind of different time periods. And these are all examples of samples from the distribution about the kind of physical state of the atmosphere. How to use kind of our learned data distribution? In practice, simply sampling from it is not that interesting. So if you imagine that I just sample a random atmosphere state that is likely according to the ERA5 dataset, this is not necessarily useful. In practice, what we want is much more specific, and that is conditional generation. So we have some kind of prior information that we know is true, and we want to kind of predict something based off this prior information. And there I will go through kind of a couple examples of what this might look like. The first and most maybe common is forecasting, where we, for instance, have the current state of the atmosphere. So this will also be called the initial conditions. We'll denote them as y in this diagram. And then we try to predict a forecast. And so we want to be able to sample from future time points of like what atmosphere states are likely. And this is a probability distribution, or we're modeling it as a probability distribution because of the chaotic nature of the system. And so yeah, the goal is kind of that our p theta x can be used to do this kind of conditional sampling. Typically, if we can do the unconditional sampling, doing the conditional sampling with neural networks is not particularly difficult because it's easy always to add another input to the neural network. Another example might be downscaling, where we have kind of a low resolution atmosphere estimate, but we want to be able to do kind of a much higher resolution estimate because that's what's useful to kind of everyday people. And this is called downscaling. And again, this is somewhat probabilistic because we're trying to kind of deduce information based on what kind of isn't in the input, but we have a kind of a good idea of what it usually looks like in practice. Another maybe more unusual example might be dataset translation. In this case, our kind of conditioning information might be some observation. For instance, in this case, I have put up the picture of a georing. So this is kind of information captured by a geostationary satellite. In fact, 3 geostationary satellites kind of concatenated together. And we might want to estimate kind of an Era 5 style state of the atmosphere from this, which can be then used for further tasks downstreams. Again, there will be some uncertainty, and so this is a probability distribution that we simply want to be able to sample from. Throughout this kind of lecture, I'll assume that you have a good understanding of neural networks, kind of the gradient-based optimizations, and so we will just assume access to a neural network, some kind of gradient-based optimizer, and some data set, or as we will usually denote it, p-data. And the kind of big question of this lecture is, with what loss function, or with what loss function will we train? Now, the kind of principled approach is kind of negative log likelihood. There's a number of ways to motivate why negative log likelihood is kind of what we want. The most common are kind of cross entropy or the Kullback-Leibniz divergence, also called the KL. Briefly, what we kind of write down is that we're trying to minimize the parameters of our neural network. This is kind of the gradient-based optimizer with respect to the kind of log probability given assigned by our neural network to each of the samples in the dataset. So this we will write down as an expectation. What is the kind of Kullback-Leibniz divergence? You can think of it like a distance functions between probability distributions. It's not technically a distance function because it lacks symmetry. So it doesn't matter in which order I put in the kind of 2 distributions P and Q into my KL that I show here on the screen. But importantly, once the KL is 0, we know that the 2 distributions must be the same. And the other kind of nice property is that it's always positive, which means if we are always kind of minimizing this KL and we eventually reach 0, we know that we've achieved our goal and we have kind of made the 2 distributions the same. Now, how do we get from the KL to the negative log likelihood? Just a tiny bit of algebra, no need to be scared, can get us there. So on the left-hand side, I've started by saying that we're trying to minimize this distance between the data distribution that we want to kind of learn to approximate and the distribution given by our neural network, p theta. So we were trying to minimize kind of the parameters of our neural network to kind of achieve these 2 distributions to be the same. If I take my definition from the previous slide, and I encourage you to kind of follow along on a piece of paper next to you, I can split the log, right? I have a kind of fraction inside a log, and so by the rules of the logarithm, I can split this with a negative sign. And so I get 2 terms. And the first term is basically the entropy of the dataset. Now, this entropy of the dataset is irrespective of whatever parameters I assign to my neural network. So in fact, when I'm trying to minimize this distance purely by turning the knobs of the neural network, it will have no impact. And so I can kind of cut it out. Technically, it now becomes a proportional. And then what remains is the negative log likelihood that I talked about initially. So we can see that when we're minimizing the negative log likelihood, we are minimizing a distance, and in fact, a Kullback-Leibniz distance between our data distribution and our neural network distribution. This sounds all wonderful. What is the problem? The problem is that probability distributions need to sum to 1, and this is a kind of a critical defining factor of a probability distribution. And in the discrete case, this is usually not a problem, because we can simply enumerate all the possible states and kind of compute their kind of mass, and then normalize kind of the mass we've assigned, kind of how likely a given element is by this kind of normalizing constant, which we'll also sometimes write down as z and call the partition function. The problem is that in continuous spaces, we need to integrate. And doing this integral over many dimensions is intractable, as many of you probably know. And so we get to the first kind of, one of the first kind of deep learning attempts to kind of get around this issue. And there's a bit of a going back to the drawing board. So modeling the continuous density directly via the negative log likelihood is hard. So what can we do instead? And because our goal is to primarily sample from the distribution and we don't necessarily need to produce the probability density directly, what we can do is we can take some random variable that we can easily sample from. You can imagine a unit Gaussian, or maybe a uniform distribution. We will denote this in this example as kind of capital Z. And we want to learn a neural network function that transforms from Z to our data distribution. Kind of being idea is this is a way to sample. We can then sample simply from our Gaussian, which can be high dimensional or can just be a single dimension. And we can then get samples from our data distribution. In terms of our negative log likelihood, what we've done is we've marginalized in Z. So we're now taking an integral over kind of the joint distribution between X and Z. And by Bayes' rule, we can rewrite this in this pz times p theta x given Z. And the way you can read this equation is that exactly what I kind of just said in words just before. We can sample from pz, and then we can put it through our neural network, and our neural network will basically learn this kind of likelihood. And with that, we are back to our principled negative log likelihood approach. The problem is the same as before. The marginal, so this integral over Z, is intractable because integrals are simply expensive, especially as you go to high-dimensional spaces. And so the variational autoencoder introduces two tricks to kind of get around this issue. The first idea is that you have an encoder that kind of tries to learn what are the important points in Z that we need to kind of optimize over. To do this, we introduce a second neural network we will call the encoder, and we will denote with Q phi, which kind of learns the posterior distribution, so Z given the input X. And so, the data points X we will put in are the data points that we really care about. And so for those data points, we want to know to what Z should they be mapped. And the second thing is something called the Jensen inequality. It will just help us with the algebra and rearranging things nicely so that we get something that we can actually solve. Now, step by step. Again, please don't be afraid. It's not as bad as it looks, and feel free to pause at any time. On the left-hand side, we start with our negative log likelihood where we've marginalized in Z. We will apply kind of Bayes' rule to kind of have pz times p theta x given Z. And then the second thing we do is that we simply multiply both the top and the bottom of this fraction with our encoder values. You can very easily see that these just cancel, so I've actually not changed anything about the quantity itself. However, what it allows me now to do is to express this integral as an expectation. And so in particular, I just view this integral as the expectation over this variable Z if I have sampled it from my encoder, and then I get this term inside. And here comes the Jensen inequality. The Jensen inequality basically says that I'm allowed to swap this log and the expectation, and that this term will then be an upper bound to this term. And because we are kind of minimizing and pushing towards 0, and we know that our KL cannot be, must be positive, so must be greater or equal to 0, our optimization process has kind of the same goal and kind of still works. We're kind of optimizing a bound on the negative log likelihood. Pushing through, we can use the rules of the log to kind of split this log into two terms. And now you can kind of see that this first term is another Kullback-Leitner distribution. And that the second term becomes this kind of negative log likelihood under the Z given by our encoder. Now these two terms seem a bit abstract as written here, but if we kind of look at them more carefully, we can see what they mean. In particular, the Kullback-Leitner has, there's this expectation over the whole data distribution outside. So this is saying that over the whole data set, the distribution given by our encoder, Q, should match that of the prior kind of PZ. So it's basically saying over the whole data set, the distribution given by our encoder should match this Gaussian that we want to sample from. And so it's basically, another way to phrase this would be that our data distribution needs to be evenly distributed in this latent space of this variable Z, so that when we sample a random Z and then kind of transform it with our neural network, we kind of cover the whole data distribution space. And so that just because I sampled a Z that wasn't hit by the encoder, I don't end up with a kind of completely unlikely sample of the data distribution. And the second term says that over the whole data set, if I encode X into this latent space and I sample from this distribution produced by the encoder, I can then decode it with my neural network, which transforms from Z to the data distribution, and that's basically kind of doesn't change the actual input X. And so this is kind of like a reconstruction loss. And this is where the term autoencoding comes from. The Q is the encoder, and P is the decoder, and so they are kind of doing this autoencoding style solution. And this term is the variational part, which kind of constrains that our latent space is well behaved so that we can kind of do the sampling process that I described at the beginning. There is kind of two final details. The first is that for our KL to be tractable, we both need these terms kind of Q and Z to be Gaussian. So what we do is we define our encoder to simply output the parameters of some high-dimensional Gaussian. So we output a mean and a standard deviation. And we can then compare it to our PZ, which is some kind of very simple Gaussian that is kind of a unit Gaussian. The kind of autoencoding loss is computationally easy, but we need to be able to backpropagate through the sampling step. It turns out that this is quite simple to do with something called the reparameterization trick. The way we sample is simply by sampling some noise, and I apologize, there's a mistake here. It should be a normal, not a uniform. We sample from this kind of uniform noise, and given the parameters output by our encoder, we can transform this into kind of a sampling procedure. This will be a valid sample from the distribution given by the encoder. And because this kind of sampling step doesn't, the epsilon doesn't depend on any of the parameters of the encoder, we can backpropagate just fine. I will kind of leave you with two summary pictures. The first is kind of from a neural network perspective. To kind of summarize what we've done, we've taken our input and we've put it through an encoder. This encoder gives us kind of the mean and the standard deviation of some distribution from which we likely think that this input sample comes from. Together, with some noise, we can kind of produce a sampled latent vector from this encoder. And then we have a probabilistic decoder, which kind of maps it back to the input space, and we can now compute how much information do we lose, how are these two samples identical, because they should be. The second kind of viewpoint is that of a probability perspective. So if you imagine your data set as some kind of low-dimensional manifold, because many kind of combinations of values for different variables, for instance, in our atmosphere, might be incredibly, incredibly unlikely. And so kind of within all the space of all the possible values for our kind of variables in the atmosphere, there's only a small number that are kind of physical. And so this is what we call the low-dimensional manifold of the kind of physical data. What happens is that we take a point from this data set, we map it through our encoder, and we map it to this kind of very kind of smooth latent space. But the encoder kind of maps the data point to one particular subpart of the data space. And here, the kind of variational constraint, this kind of KL, kind of ensures that we cover the whole Z space, so that when we kind of sample from Z, we can go through our decoder and we map back to the kind of data distribution. Now, getting on to score matching / diffusion. I kind of told you why VAEs are kind of so nice and kind of showed you why they kind of do in principle exactly what we want. But in practice, they're not kind of state of the art anymore. And that's because it tends to be difficult to learn good encoders and decoders. You need very flexible neural networks as encoders and decoders to be able to satisfy both the KL constraint and the reconstruction. And it's not necessarily always easy to find them with your gradient-based optimizers. And so what happens in practice is you tend to get slightly blurry pictures, which is not ideal. And so there's a different idea, and this is called score matching. And the kind of idea is that I can walk around the kind of probability distribution in this, with gradient descent, kind of the same way I can do a neural network optimization. The kind of probability density will be highest at the data points that I actually want to sample. And so I can just follow the gradient of the probability distribution to kind of end up on the modes of my probability distribution. The modes would be these kind of, in this example, these three kind of hills. And so a way to sample from a probability distribution is to simply randomly take a sample in space and then follow the gradient of the probability distribution, and you're basically climbing up the kind of probability density function until you end up at some kind of a probability density that is kind of meaningfully high enough, and so you have a likely data sample. And so this is what we will call the score. And so basically it is the kind of derivative of the kind of log probability with respect to the input, so with respect to x. And why does this work? And this is the question you all should be asking. If I have my neural network, and I assume for a moment that I can kind of parameterize it as some kind of Boltzmann distribution. So my neural network F kind of produces a number for each kind of sample for kind of how good is the sample, and then I compute some kind of normalization constant Z, this kind of partition function. This partition function is an integral over all the possible input points x, so it only depends on the parameters of the neural network. So what happens when I look at the gradient with respect to x is that this term ends up being 0. And so, in fact, to be able to follow the gradient of the probability distribution, I don't need to normalize anymore. And so this means that we don't have to deal with this pesky partition function that is intractable to compute. And so we're very happy. And so the last kind of final question is, how do we estimate the score? And the answer is that we kind of learn to denoise. So we have samples from p data, but we don't have access to the derivative of the log probability of the sample. What we can do is that we add a tiny bit of noise around each data point. And so the way we can write this down is as kind of q, which kind of produces some x tilde, where there's kind of a Gaussian centered around our data point x coming from p data. And now we can kind of take the gradient of the log of this, and we can do some algebra that kind of gives us a loss function that we can compute. So in particular, because the Gaussian is kind of has a kind of analytical form, we can just put this in. The log means that things become kind of nice. The kind of this normalizing element of 1 over sigma times the square root of 2 pi is some kind of constant, so we can kind of drop it. And then we are kind of left with the kind of gradient of what's in the power of the exponential, because the log and the exponential nicely cancel. And so computing this, we get kind of a very simple and nice mean squared error loss that basically says that we want to take our noise sample x tilde, and we want to go back towards the original data set. So our score function is basically learning how to kind of denoise the input. And this is why it's called denoising score mashing. And you can show that in the limit, as we add less and less noise to each data point, this will indeed recover you the derivative of the log probability of the data. And so we're kind of learning the direction of the data manifold. Again, in the real world, it's a bit pesky and there's some problems. And in this case, the problems is the low probability area. Remember in the VAE picture how I drew the kind of data distribution as this kind of funky low-dimensional manifold. And in fact, a lot of the kind of space, the data is so unlikely that we get very poor estimates of the score, of the probability distribution. So if you imagine that I have a data density with kind of 2 modes, these 2 modes are kind of unequal, so this might be much more likely than this. You can imagine this saying, for instance, in a forecasting problem, tomorrow is very likely to be sunny, but there is a small likelihood for a very bad storm. Now, if I sample random states of the atmosphere, a lot of them are very far from kind of a physical state of the atmosphere. And because we have never seen this during training, we have a very poor estimate of where the kind of actual modes are. And in principle, what this means is when I'm already close, when I've already sampled close to a physical point, then I have accurate estimates of the gradient and I can really make this a sharp, accurate physical estimate. But when I'm far away from it, I have no chance to get there. The other problem is that basically the mode I end up with is kind of determined by where I started. So if I kind of just randomly sample in this space and then follow the gradients, if I have this very large kind of valley, kind of like just very flat land, then there is no gradient that tells me where the next hill is. Which means that if I start close to this hill, I just end up on this hill. I will never go to the kind of further away mountain. And kind of similarly here. And so you can see that if you just kind of have this kind of low, kind of poor estimates of the kind of distribution in between, you kind of will equally sample these 2 modes. And the solution is doing this kind of what is called annealing. What is this annealing? It's basically saying that you add different levels of Gaussian noise. And this tends to be the solution to both problems at the same time. So to estimate the gradient of the log distribution, we added a little bit of noise and we called this denoising. And we said that when we add very little noise in the kind of limit, we will get an accurate estimate of this gradient, of the score. What we can also do is that we can just learn kind of a score function, like our neural network that learns the score, at different levels of noise. Which means that sometimes we add a lot of noise to the data. What this does, it means it kind of spreads out the data in kind of space. And at this point, we can now see that we will get accurate estimates of the kind of gradient back towards the data manifold. Because the gradient is kind of because the Gaussian, is much larger around the data point, we can estimate back to the center of the Gaussian from much further away. Obviously, if we had kind of two small different modes here, they would be completely look as one mode. And this is why we have noise at different kind of noise levels. So we might start kind of following the gradient in this kind of high noise level so that we end up kind of broadly in the right quadrant, kind of the bottom left and the top right quadrant. And then we look at kind of the same kind of gradients, but at a bit less noise. And now we will get kind of closer and we can kind of repeat this as often as we need to. And this happens to work very well in practice. So the kind of final score matching function is kind of exactly the loss function we had before, kind of the mean squared error between our estimate of the gradient and the kind of gradient we compute from adding a bit of noise to the data. But we now do this at many different noise levels. And so we kind of have a loss function that takes in kind of at what noise level are we kind of computing this kind of particular score. And we can do some different weightings. And yeah, the different weightings can help in practice kind of as an additional knob to get very nice, sharp pictures. And this worked incredibly well. And so at inference time, what we do is that we take some random noise in our physical kind of space in kind of the same dimension. And then we kind of use our neural network, tell it at the kind of highest noise level, kind of follow the gradient. And so we follow this gradient a bit randomly. So we sample some noise and we kind of randomly will follow kind of the gradient of the data distribution. So this is kind of like the stochastic gradient descent. We do this first at the kind of coarsest noise level, so at the kind of most smoothing noise level. And then after a few steps, we move up to the next noise level. We continue taking a few steps and so on and so forth. And by the end, we will get kind of sharp, clear pictures that kind of follow the original data distribution. Now, there was an interesting insight made by researchers that this is actually very closely related now to diffusion, and it's kind of sort of a VAE. So let's briefly introduce this kind of perspective. Because we now have these different noise levels, we can also kind of view going from one noise level to the other as some kind of Brownian motion. And so what kind of happens is that each of kind of the noise levels is kind of some kind of latent variable where we've added a little bit of noise to kind of the original data distribution. And so this is sort of like an encoder. But instead of having just a single latent variable that we map to in kind of one single neural network, we now do this very repeatedly. The different noise levels each represent a kind of latent space. And this is kind of like a hierarchical variational autoencoder. So Q is our encoder, but instead of having any parameters, it's just adding noise. And what we've done is we've learned kind of how to go back from one noise level to the next. And this is kind of what we learned. And this is kind of this denoising that we also learned in the score matching. And it turns out that with diffusion, you can get a kind of very nice theoretical foundation for how you should choose your noise level, which previously in score matching we kind of did ad hoc. And so this is why diffusion has kind of taken over. There's a couple kind of key differences. In VAEs, there was mutual information being conserved, right? So because we did it in one shot and we had a neural network and it kind of gave you a different Z and a different distribution in this latent space for each input, there was mutual information that was kind of remaining between our input and our kind of latent variable. This is no longer the case because our encoder has no more parameters and it's just destroying information. It turns out that this makes it actually a lot easier to learn a good decoder through this kind of hierarchical process at the cost of not having a good encoding of our neural network, of our good encoding of our data in a lower dimensional space. Now, this is some detailed math. Don't worry if this is a a bit too much at the moment. I hope that you primarily got the kind of high-level idea. So kind of previously we marginalized in a single z, and now we will marginalize in kind of many z's. So this is x1, x2, x3, xt. Each of them kind of being a latent variable that we don't have access to, but we can generate samples of. We can kind of factorize this as before in this kind of autoregressive way, because we've defined our kind of noising process to be step by step. And so xt only depends onto xt minus 1. So we define each kind of noising step as some kind of Gaussian, so we add some kind of Gaussian noise to the input. And so we can kind of define p xt minus 1 given xt also as some kind of Gaussian. So we kind of take some Gaussian step to also denoise. And so at each step, we kind of predict the parameters of Gaussian that is going to be slightly less noisy than the previous step. And we can use the same machinery, same kind of Jensen inequality as we did in the variation autoencoder. I leave this as an exercise to you. If you want, there's kind of many papers that kind of will walk you through this math, and so you can kind of look them up and check your answer if you'd like. But we can kind of get the same kind of principled loss function and connect it back to the negative log likelihood. And this is kind of very nice to give us kind of a bit of confidence that what we're doing is actually theoretically well motivated. In practice, kind of if you derive it by hand, you will get very specific weightings between each of the noise levels. In practice, we throw most of these weights away, and we just kind of randomly sample noise levels, and we'll just kind of compute the denoised or the noise that we was added. And what will really matter is kind of the schedule at which we add noise. So kind of things that I've swept under the rug is how do we choose the noise to add? How do we best choose a neural network architecture, and what kind of optimizer works best? The reason I've kind of chosen not to talk about them here is that because in practice, they get updated all the time. Like every few months, you get a new paper saying, oh, this is the best noise schedule to use for this particular problem, or this neural network architecture works a bit better for this particular example. And so this is something I would just encourage you to look up most recently, what's kind of been shown to work best, or kind of talk to your colleagues that have experience with this. Finally, getting a bit more concrete again, when we apply this to weather forecasting, what does this look like? This was also explored in AIFS, but this was the nicer diagram to kind of show you. And the idea is kind of very similar. We kind of have our previous state. So this is our kind of conditioning information, which we will call x0. And then we have a neural network that will kind of learn this kind of denoising or diffusion style kind of update to the input. So the input will be the conditioning information as well as some kind of random noise on the sphere. And at each step, this neural network, R theta, kind of solves and denoises the kind of next input until we've kind of predicted x1, which will just be one sample. So we can repeat this process repeatedly and get different samples for our forecasting. At each step, we need to move forward in time, and we can do this again. And then this way, we can kind of get probabilistic forecasts. Note here, you can immediately see kind of one of the downsides. We need to do many neural network evaluations to just get a single sample from the next possible step. So if we want to kind of predict many possible future weather states, there's a lot of neural network kind of forward passes that we need to go through. And this is kind of the main downside of something like score matching or diffusion, is that it is very expensive at inference time, which is why in kind of newer generative models, such as AIFS, they've moved on to a different generative model called CRPS. Unfortunately, I won't have time to talk about in this lecture. Thank you very much for listening. I'll briefly show some of the kind of references used in this talk in case you want to do some further reading. Thank you very much.